All right, so arc length. When we talk about length in any geometric setting, we typically use the formula at the top, which is very much familiar, hopefully, to you. This is the distance formula. It's taken from the Pythagorean theorem, but it's the square root of x2 minus x1 squared plus y2 minus y1 squared. And conceptually, we're using the same idea as when we first started out and did rectangles under the curve. And if we add up all the rectangles, then we'll get close to what it is. And if we have an infinite number of rectangles, then we'll have the perfect amount under the curve, right? So conceptually, this is the same idea. If I want to find the arc length of this, now if I were doing the arc length on a circle, that's easy because we know that it's the percentage of the circle, and then I have a formula to find the circumference of the circle. But when it's under a curve that is not a specific shape, geometric shape, then we have to introduce calculus. So we start by introducing precalculus. If I want to estimate this, well, I could take the distance from these 2 points and add it to the distance from these 2 points, and then add it to the distance from these 2 points, and so on and so forth. Okay, and the more tiny segments that I have, the closer I get to the actual length. And if I could do an infinite number, then I would have the actual length of my curve there. And so that's where this formula was developed. This is the definition of arc length, so this is one that you will want to memorize. This is just in terms of x or in terms of y, depending on how it's written. Let the function be given by y equals f of x represent a smooth curve on the interval a, b. The arc length of f between a and b is your boundaries a to b, square root of 1 plus the derivative of your function squared. Okay? The derivative of your function squared. And then the same thing for the y. The y is just if it is in terms f of y equals something. So depending on how you've been handed the graph is how you're going to do this. The first one we're going to do is actually I just like it, and we're just going to walk through it. It is this one right here. Example 1. Find the arc length from x1, y1 to x2, y2 on the graph of fx equals mx plus b. Mx plus b should be vaguely familiar. That is a linear graph, right? And so I am going to take my definition that they just gave me, and I am going from x1 to x2 because that's what they told me to do. If I'm doing my x's here, it's in f of x, so I do want to use my x's. And I want to go 1 plus the derivative of my function squared dx. Now, the derivative of this function, my b will drop off because it is just a constant. And then the derivative, so f derivative of x should just be m. What is m in a linear equation?
Slope.
It is slope. So how do I find m in a linear equation? What's my formula for m? x2 minus x1. There we go. All right. And so I am actually, if my derivative is m and this is m, I'm going to plug that in for my derivative. So I'm going to say, well, from x1 to x2, the square root of 1 plus this y2 minus y1 over x2 minus x1 squared. All right. So I'm going to get a common denominator here, right? So my common denominator is going to be, like if I were to take this piece, it's just y2 minus y1 squared over x2 minus x1 squared. That's what happens when I square a fraction, right? I square the numerator and square the denominator, correct? And so if I want a common denominator between that and the 1, it's going to be the x2 minus x1 squared. So I can rewrite that inside to be x2 minus x1 squared plus y2 minus y1 squared all over x2 minus x1 squared. Right? Does that make sense? Okay. And this is, if I were to take my antiderivative of this function this is not necessarily a function. These x2 and x1s represent numbers. So that whole great big thing there is just a number. So what's my antiderivative of a number?
It's just a number.
It's just a number times x, right? So if this whole group here represents a number, some number, because x2 and x1 are actual constants, right? They're numbers. So this whole thing doesn't have an x in it as far as functionality goes. Those just represent numbers. So it would be like saying 3 dx or 4 dx. That's just a number. And so if I were to take the antiderivative of a number, it's that number times x. So the antiderivative of this, and you'll see that in the book there, I'm going to shift it up a little bit. The antiderivative of this is just this whole thing right here, the square root of x2 minus x1 squared plus y2 minus y1 squared all over x2 minus x1 squared times x. All right. Yes? And I'm doing that from x1 to x2. It'll make more sense in just a second. So, if on the left-hand side, my numerator doesn't have a perfect square, okay? So I am going to just leave it as the square root of x2 minus x1 squared plus y2 minus y1 squared. I'm going to leave that. On the bottom, I have the square root of a square. Does everybody see that? That group is squared. So it just becomes x2 minus x1, right? Because I had a square and a square root. And then for this piece, the x, I need to plug in my x2 and x1 and subtract them. That's how I do antiderivatives. So I'm going to plug in my x2 minus x1 there for x, because those are my two numbers that I'm putting in. Now, I can cancel something, right? I can cancel these. My answer to this is just x2 minus x1 squared plus y2 minus y1 squared. That looks vaguely familiar. What is that? Distance formula. What would I use if I wanted to find from here to here? That's the change, right? That would be the arc length, would it not? The arc length from there to there would be distance formula. When you plug it into your calculus equation, you get the distance formula for a line, which is what you would do for a line, the distance formula. So when you use this long derivative process with something you already know how to do, you're still going to get, and this is actually the formula you would use. You get the formula you would use for a linear graph, which is just x2 minus x1 squared plus y2 minus y1 squared. What I like about this is they take something that we're familiar with. If I just said find the length of that line, you would go straight to distance formula, and they apply the calculus to show you using this formula gives you what you would do for this. And so therefore you can see that it's going to work for an arc when I do it with an arc as well. All right, so let's look at the arc. I love that they gave us like this crazy function here. All right, so when you're finding length of an arc, your first step is really to find the derivative of the function they gave you. Because you're plugging in, I put the formula back up here so you could see it. You're plugging in the derivative when you use this, okay? And so the first thing I want to do is I want to take this, and I'm going to rewrite it a little nicer, 1/6 x cubed plus 1/2 x to the negative 1. I just rewrote what they gave me there. And so I want to find my derivative of this first. Find the derivative first, because the derivative is what you plug in. And so my derivative is going to be 3 times 1/6, 3/6 or 1/2, x squared. Remember, you go down. And then -1 times 1/2, -1/2, right? And then you go down x to the -2. That is my derivative, right? And that's what I will plug into this equation that they've given me. And so now that I have found my derivative, first step, find derivative. Then you can plug in your 1/2 to 2, which is what they told you. 1 plus this crazy thing squared. And I'm going to leave it like this, just so when we take the antiderivative, it'll be easier, because we are going to have to take the antiderivative as well. So 1 plus, and we're going to say 1/2 x squared minus 1/2 x to the -2 squared dx. This is where you're going to look for perfect squares, okay? So by that I mean we want to make this a little more simple than what we have. So go ahead and FOIL this out. So if I FOIL this out, I get like 1/4 x to the 4th, and then we get multiplying these two together and doubling it. So x squared and x to the -2 is x to the 0, which is 1, right? And then we get 1/2 and 1/2, which is 1/4. And then we double that. Does that make sense? So when we FOIL this, you're going to multiply these together, 1/4 x to the 0, and double it. So 2/4 x to the 0, or 1/2, right? And then you would get 1/4 x to the -4. All right, so that's what happens when I FOIL it, and I still have this 1 plus right there. All right. So far, so good. All right, so I'm going to combine like terms here. I'm just going to do a little bit of algebra. 1 can combine with the -1/2. So I end up with 1/4 x to the 4th plus 1/2 rather, and then plus 1/4, and they have it over, so we have 1 over x to the 4th. Right. Now you probably won't, you may not see this exactly. When you have fractions like this, you probably want to pull out a fraction so that you can look at it a little bit easier. So if I take a fraction out of this, 1/4, right? I get x to the 4th. What happens when I divide 1/2 by 1/4? Yeah, so 1/2 times 4. So you get 2. And then this, I took out the 1/4, so I just have the 1 over x to the 4th. This is a perfect square trinomial. It's not the prettiest perfect square trinomial in the world, but it is a perfect square trinomial. So we end up with 1/2 to 2. We have 1/4. And then this guy right here is going to be x squared plus 1 over x squared squared. So I have the first term is a perfect root, right, x squared. The last term is a perfect root, 1 over x squared. If I multiply these, I get 1, and double it, I get the center. That's a perfect square trinomial from way back in Algebra 1 and Algebra 2 days. It's a perfect square trinomial. So I end up having the square root of 2 perfect squares, right? 1/4 is a perfect square. So I have 1/2 to 2. 1/4 is a perfect square. That's 1/2, right? And this is a perfect square. X squared plus 1 over x squared dx. So we're going to move these guys out of the way. Oh, they won't move. I'll just highlight him. So this right here is what I have to take the antiderivative of. I know y'all thought I was done. The 1/2 can just come out, right? That can come out 1/2. The antiderivative of x squared is 1/3 x cubed. The antiderivative of 1 over x squared, that's x to the -2, right? So we add 1, which is -1, and we divide by our new. So this is going to be minus 1 over x. And we're doing that from 1/2 to 2.
How did you get from the paper?
Plugging in's not beautiful, but it is what it is. So when you plug it in, I mean, I feel like the example they gave you was like the worst of the worst. Fractions with a perfect square trinomial with fractions and what you're plugging it into, but that's okay, we'll forgive them. So I plug in a 2 and I get 8/3 minus 1/2. And then I plug in a 1/2 and I get 1 over 24, right? 1/8 times 1/3. Minus 2, 1 over 1/2 is 2. And I believe when they said it's all said and done, we get 33 over 16. And I'll double check that just to make sure all of our numbers are right. Always looks daunting. The original is y equals the natural log of cosine of x. All right? Remember derivative of natural log, because the first thing we want to do is take the derivative of this. So we want to find y prime. Derivative of natural log is just the derivative of the inside. So what's the derivative of cosine? Negative sine over the derivative of, just the function itself, cosine. How can I rewrite that? Negative sine over cosine. Negative tangent. So that's what I'm going to plug into my formula. So I'm going to say, they told me it was from 0 to pi over 4. And I'm going to say 1 plus my negative tangent of x squared. This should look familiar, 1 plus tangent squared. What is 1 plus tangent squared? It's a Pythagorean identity. Secant squared. So I really have from 0 to pi over 4 of the square root of secant squared. Well, that makes my life so much easier, doesn't it? Because it's really just secant of x. The square root of a square is just the function, right? I do have, this should be one you've memorized. And the integration of secant is the natural log of secant plus tangent. Hopefully that's memorized. So we have the antiderivative of that is going to be natural log of secant of x plus tangent of x from 0 to pi over 2. When I plug in a pi over 2, secant of pi over 2, that is 1 over, pi over 4. 1 over my cosine. Cosine of pi over 4 is just square root of 2 over 2. So you end up with the reciprocal of that. So 2 over the square root of 2. And then you multiply top and bottom. And the 2's cancel. So the secant here is just square root of 2. The tangent of a pi over 4 is always 1. Because it's square root of 2 over 2 over square root of 2 over 2. So we have the natural log of that. And then we have to subtract the natural log. Secant of 0, that is 1 over your cosine. Your cosine at 0 is 1. So secant of 0 is just 1. And then tangent of 0 is 0. So we just have natural log of 1 there. And when you plug that in, they actually did a calculator, so it's 0.8814 as your answer there. So they're not all crazy and big like the first one they gave us. It's really, when you're doing these, your very first step, so step 1 is to find the derivative. Find your derivative. Then step 2 is to plug it in and then to integrate. Right? Integration. So find your derivative first, plug it into your formula, then do your integration.